There are these substances that are so powerful that nothing stands in their way. They eat through metal, they ignite on contact, they break down living tissue in seconds. Every one of them is real, and they're backed up by science. These are 20 substances that truly destroy almost anything they touch. Starting with number 20, Aqua regia. Aqua regia, Latin for royal water. It's a highly corrosive mixture and it's made by combining concentrated nitric acid and concentrated hydrochloric acid, typically in a ratio of 1:3. Yeah, that would be pretty bad. Each acid is already dangerous on its own, but when mixed, they create a reactive solution capable of dissolving some of the most chemically resistant metals. The destructive power of aqua regia comes from a combination of things. Nitric acid is a strong oxidizer. It can convert elemental gold atoms that are normally extremely stable into gold ions by removing electrons. However, gold ions alone would quickly revert back into solid gold. This is where the hydrochloric acid comes in. It provides an abundance of chloride ions that immediately bind with oxidized gold to form tetrachloroauric acid, a stable soluble complex. Because the gold ions never get the chance to revert to solid metal, more gold atoms continue dissolving. This two-step mechanism, oxidation plus complexation, is thoroughly documented in organic chemistry, and it explains why neither nitric acid nor hydrochloric acid alone can dissolve gold, but together they can. Aqua regia also produces several highly reactive gases. The fumes of these are dangerous and corrosive, like chlorine gas, and their formation contributes to this destructive behavior. The solution's not stable for long, and over time it breaks down as the reactive gases escape. It is one of the few substances that can strip metallic contaminants off of glass without really damaging the glass itself. However, the fumes can corrode metals in the surrounding environment, so proper ventilation is essential. One well-documented historical use of it happened during World War II. When the Nazis invaded Denmark, a chemist dissolved the gold Nobel Prize medals of two German physicists using aqua regia. The solution was left on a shelf in the Niels Bohr Institute and ignored by occupying soldiers, and after the war the dissolved gold was recovered from the solution and recast into new metals. The story is widely reported, and it shows both the power of aqua regia and its unusual ability to dissolve gold completely. But despite its destructive nature, it can affect everything. Certain plastics and glass and ceramic materials remain unaffected, and contact with organic solvents can lead to dangerous reactions, and mixing aqua regia with certain compounds can produce explosive byproducts. Number 19. Fluoroantimonic acid. Fluoroantimonic acid is often described as one of the strongest known superacids. It's created by combining hydrogen fluoride with antimony pentafluoride. This resulting mixture isn't simply acidic, it's orders of magnitude stronger than pure sulfuric acid. In fact, its proton-donating ability is so high that it can protonate substances that normal acids can't even affect, including hydrocarbons like isobutane. Its acidity has to be quantified using the Hammett acidity function, where values of -20 or lower have been recorded, making it millions of times stronger than concentrated sulfuric acid. Now, it's not a fixed compound, but a family of mixtures with varying ratios. Despite its reputation, the acid doesn't melt through everything. This is a common misconception. The reason is pretty straightforward. The reactivity depends on chemistry, not on the corrosive power in a generalized sense. For example, it has to be stored in Teflon containers, not because it can't react with Teflon, but because Teflon's carbon-fluorine bonds are among the strongest in organic chemistry. On the other hand, the acid reacts violently with water, releasing heat and producing toxic hydrogen fluoride gas. This acid can decompose or react unpredictably when impurities are present, and for this reason it's handled under inert conditions, often inside dry glove boxes with specialized equipment. Researchers working with it have to rely on strict procedural controls, and incidents involving it are rare because of these precautions. There is no speculation about its classification. It is, by all available data, one of the strongest protonating agents ever synthesized, and its destructive behavior is specific rather than universal. It destroys many substances instantly, but it leaves fluorinated materials unharmed. Number 18. Piranha solution. Piranha solution, this is one of the most aggressive cleaning mixtures used in laboratories. It's known for its ability to destroy almost any organic material it touches. It's typically a mixture of concentrated sulfuric acid and hydrogen peroxide, usually to a ratio of about 3:1. When the two chemicals combine, the hydrogen peroxide decomposes rapidly and it generates a highly reactive oxygen species. This process is strongly exothermic, meaning it releases a large amount of heat, and as a result the mixture can reach temperatures well above 100 Celsius within seconds, even without external heating. Concentrated sulfuric acid alone is a strong dehydrating agent. It's capable of stripping water out of organic materials. When hydrogen peroxide is added, it produces peroxymonosulfuric acid and other highly reactive intermediates. These oxidants attack organic molecules immediately and they break carbon-hydrogen bonds and produce carbon dioxide, water, and heat. This is why the solution can remove baked-on residues from glassware that ordinary solvents can't touch. And unlike many strong acids, this Piranha solution doesn't rely on acidity to break down materials. The oxidative compound is so strong that many organic compounds are just destroyed on contact, often with vigorous bubbling or even violent reactions. Experimental demonstrations show that placing a piece of paper or a cotton swab into freshly mixed Piranha solution results in near-instant charring, followed by rapid decomposition. Importantly, Piranha solution doesn't destroy everything. Inorganic glass like borosilicate glass, certain ceramics, and some fluorinated plastics do resist attack, and this is why those materials are used for preparation and handling. Every aspect of its behavior, the heat release, the oxidative strength, the reactivity with organic compounds is well studied and documented, and there's no uncertainty about what it can and can't do when it's mishandled. It's a real, extremely powerful oxidizing mixture that must be respected in any lab environment. Number 17. Hydrofluoric acid. Hydrofluoric acid, it's one of the most dangerous industrial chemicals, not because it's the strongest acid, it isn't, but because of the specific way it reacts with both materials and human tissue. It's a solution of hydrogen fluoride gas that's dissolved in water. Unlike many mineral acids, hydrofluoric acid can dissolve materials that are normally considered acid-resistant, including glass, silica, and many metal oxides. It attacks metals in a unique way. While some strong acids just simply corrode the metal's surface, hydrofluoric acid reacts with metal oxides and forms stable metal fluorides, which can continue dissolving the material underlying it. This makes the acid effective in things like stainless steel pickling and high-purity metal preparation. And so hydrofluoric acid has to be stored in plastic containers like polyethylene because it corrodes glass and many metals. Now, what makes it really hazardous, though, is its interaction with biological tissue. It doesn't simply burn the surface of the skin like a typical acid. Instead, fluoride ions penetrate deeply into tissue and bind strongly to calcium and magnesium ions within the body. This will disrupt cellular function and, in severe cases, lead to hypocalcemia, a potentially fatal condition where the blood calcium level falls dangerously low. Hydrofluoric acid fumes also pose a respiratory hazard. Inhaling it can cause chemical burns inside your lungs and lead to pulmonary edema. All these dangers are recorded in industrial safety standards, including those by OSHA. But it doesn't destroy everything. For example, some fluorinated plastics and specific alloys do resist any attack, but a combination of deep tissue penetration, reactivity with glass and silica, and the ability to break down otherwise resistant materials gives it a reputation that's unmatched by more typical acids. It's one of the few chemicals where both material science and medical toxicology agree. Contact has to be avoided at all costs, and every exposure has to be treated as serious. Number 16. Sodium metal. Sodium metal. I'm sure you've seen the videos on YouTube. It's one of the most reactive common elements, and its destructive behavior is most dramatic when it encounters water. Sodium is an alkali metal. It sits in group 1 of the periodic table, and all alkali metals do react vigorously with water. Sodium's reaction is especially violent because it combines rapid oxidation, hydrogen gas formation, and heat release in a single step. When it comes into contact with water, the metal immediately begins to oxidize. Each sodium atom loses an electron, forming sodium ions. These electrons reduce the water molecules to form hydrogen gas. This chemical reaction is strongly exothermic, meaning it releases substantial heat. That heat is sufficient to melt the sodium metal, so instead of remaining a solid chunk, the sodium becomes a small, mobile, liquid ball that skitters across the water's surface. This behavior has been filmed and analyzed in controlled laboratory settings too. The heat also ignites the hydrogen gas that's forming, causing flames or small explosions depending on the amount of sodium present. Studies published have shown that the reaction includes a Coulomb explosion, which is an effect. As sodium atoms lose electrons, the metal surface becomes temporarily charged, which causes repulsion between the atoms, which leads to rapid fragmentation. This fragmentation increases the surface area that's exposed to the water, and in doing so it accelerates the reaction even further. Sodium does also react destructively with other substances. When exposed to moist air, it forms sodium hydroxide and sodium carbonate, both of which are corrosive. And this means sodium has to be stored under mineral oil or an inert gas atmosphere to prevent any accidental ignition or gradual decomposition. Industrially, sodium is used in the process that takes advantage of this reactivity. It plays a role in organic reductions, such as the Birch reduction, in some metal production, and in specialized heat transfer systems like in nuclear reactors that use liquid sodium as a coolant. Engineers have to ensure that the metal never contacts water or air, because such contact would be catastrophic. Sodium does not destroy everything. Its reactivity is specific to water, oxidizing agents, halogens, and moisture. But in those environments, this destruction is rapid, energetic, and pretty well known in chemistry. Number 15. Chlorine trifluoride. Chlorine trifluoride is one of the most reactive and destructive industrial chemicals ever synthesized. Its behavior is so aggressive and unpredictable that only a small number of specialized industries even use it. CIF3 is a powerful oxidizer, way stronger than oxygen. It can ignite metals that normally considered non-flammable. One of the most famous statements about chlorine trifluoride comes from a 1950 report by the German chemical agency IG Farben. The report describes it as capable of igniting sand, asbestos, and other materials normally considered incombustible. Now, this does kind of sound like an exaggeration, but it's not. It's so reactive that it oxidizes materials on contact without needing an ignition source. It can set fire to concrete, soil, and even the residues left behind after an earlier fire. Chlorine trifluoride reacts violently with nearly all organic materials, including rubber, wood, textiles, and plastics. And when it contacts water, even in small amounts of moisture in the air, it can decompose rapidly, producing hydrogen fluoride and chlorine gas. And both of those are toxic and corrosive. One incident that was well documented happened at a chemical plant where chlorine trifluoride leaked onto a concrete floor. It reacted so strongly that it etched deep into the concrete, destroying several centimeters of material. The reaction did also release corrosive fumes that damaged nearby equipment, and the event is frequently cited in chemical engineering safety courses. And it's not anecdotal, it's included in hazardous material case studies too. Because it reacts almost with any container material, it can't be stored in ordinary metal tanks. It does form a thin protective fluoride layer on certain metals like nickel that prevents further reaction, provided the metal surface remains perfectly clean and undamaged. If that protective layer is scratched, the chemical can eat through the metal beneath. And these properties are described extensively in industrial handling specifications. But despite its danger, it has specialized uses. The semiconductor industry uses it for cleaning chemical vapor deposition chambers without needing to heat them. In those controlled environments, it breaks down the silicon-based residues efficiently, and it was also investigated as a potential rocket propellant oxidizer due to its extremely high reactivity, but the hazards are way too severe for practical use. Chlorine trifluoride does not destroy absolutely everything. It is stable against pure fluorinated materials like PTFE, but its ability to burn materials that normally cannot burn makes it one of the most dangerous substances ever handled by industrial chemists. Number 14. White phosphorus. Now, while white phosphorus is a highly reactive, waxy, solid allotrope of phosphorus that ignites spontaneously in the air, it can burn through organic material with great efficiency. White phosphorus consists of molecules which are strained and unstable. This strained structure is the primary reason the material reacts so aggressively with oxygen. At room temperature, the white phosphorus slowly oxidizes when exposed to air, and as it oxidizes, it generates both heat and thick white fumes composed primarily of phosphorus pentoxide. If the heat generated by oxidation can't dissipate quickly enough, the phosphorus reaches its autoignition temperature, about 86 degrees Fahrenheit, and it bursts into flame. These flames are extremely hot and produce dense white smoke, which is why the substance has to be stored under water or in inert gas at all times. This isn't a precautionary preference, it's an absolute requirement. Once it's ignited, it burns at temperatures that exceed 1300 degrees Celsius, that's 2300 degrees Fahrenheit. It's hot enough to char or consume most biological tissues rapidly. Medical literature describes the white phosphorus burns as deep, persistent, and capable of reigniting when exposed to oxygen, since the embedded particles continue to react. The burn mechanism is well understood. Tiny pieces of phosphorus remain lodged in the skin and reignite upon contact with air. This phenomenon has been recorded in multiple case studies and requires surgical removal of all phosphorus particles to prevent continued damage. Despite its dangers, though, white phosphorus does have legitimate industrial uses. It's used in the manufacture of phosphoric acid and phosphorus trichloride, and various chemical intermediates. It plays a role in producing fertilizers, matches, and specialty compounds. Historically, white phosphorus was used in matches, but that practice ended after its severe toxicity became known. Chronic exposure can cause a condition called phossy jaw. This disease caused disintegration of jawbone tissue due to inhalation or ingestion of phosphorus vapor. These medical records remain pivotal in the history of occupational safety. White phosphorus does not destroy everything it touches. Metals like steel or aluminum withstand its contact when no ignition happens, but its extreme reactivity towards oxygen and organic matter makes it one of the most destructive chemical substances in practical use. Number 13. Bromine. Bromine is a dense, dark reddish-brown liquid at room temperature, and one of the few elements that is liquid under normal conditions. It's highly reactive, corrosive, and it's capable of destroying a wide range of materials it comes into contact with. Like chlorine and iodine, it readily forms strong bonds with many elements, but its liquid physical state gives it some greater mobility. The element has a strong tendency to oxidize materials and substitute into organic molecules, which means it can degrade plastics, rubbers, organic tissues, and many metals. One of bromine's most immediate hazards, though, is the corrosive effect on human tissue. Contact with liquid bromine causes severe chemical burns, and prolonged exposure can result in deep tissue surgery. Bromine vapor is also dangerous. Inhalation will cause significant respiratory irritation, pulmonary edema, and chemical pneumonitis. These effects are medically documented and they're included in occupational exposure guidelines from OSHA and NIOSH. Organic materials are susceptible to bromine attack. It can react with oils, solvents, and polymers through a process called electrophilic substitution and addition reactions. This causes discoloration, cracking, or a complete breakdown of materials. Rubber gaskets and seals exposed to bromine will often degrade rapidly, which is why the equipment in bromine handling facilities uses completely different sealants than ordinary chemical plants. Despite its destructive reactivity, though, bromine has several essential uses. It's used in flame retardants, pharmaceuticals, photographic chemicals, and certain types of water treatment compounds. Storage tanks have to be sealed and often refrigerated to reduce any vapor pressure, and workers are trained specifically for bromine hazards and emergency response procedures, including neutralization steps and reducing agents like sodium thiosulfate. But bromine doesn't destroy everything. Glass and certain fluoropolymers and high nickel alloys do resist attack, but its ability to degrade metals, polymers, and biological tissue makes it one of the most corrosive and destructive liquid elements. And due to its reactivity, exposure has to be avoided at all costs, both in industrial and laboratory settings. Number 12. Fuming nitric acid. Fuming nitric acid. It's often abbreviated as RFNA, which is red fuming nitric acid, or WFNA, which is white fuming nitric acid. It's one of the most destructive oxidizing liquids ever produced. While regular nitric acid is already a strong oxidizer, the fuming varieties contain way higher concentrations of reactive species, giving them the ability to corrode, burn, or completely destabilize many materials on contact. Now, the fuming characteristic refers to the visible reddish or white vapors that form above the liquid surface. These fumes are nitrogen dioxide or nitric oxide, both of which are corrosive, toxic, and oxidizing. Inhaling these vapors pose a serious health hazard. When fuming nitric acid touches an organic material, reactions are often violent. The acid can nitrate organic compounds, which produce unstable intermediates capable of decomposing explosively. The combination of acidity here and oxidizing strength make the liquid extremely dangerous to handle without specialized equipment. Metals do react aggressively with functioning nitric acid. Iron, copper, aluminum, they corrode rapidly, producing metal nitrates and nitrogen oxides. Even stainless steel degrades unless special high-nickel alloys or fluoropolymer linings are used. Fuming nitric acid has a long history in rocketry as a component of hypergolic propellants, fuel oxidizer pairs that ignite spontaneously on contact. RFNA has been used with fuels like dimethylhydrazine and aniline. These propellants are valued for their reliability and storability, but their extreme toxicity and corrosiveness eventually pushed much of the aerospace industry towards safer alternatives. Declassified military and NASA documents from the mid-20th century describe in detail the hazards associated with these rocket oxidizers. In laboratory settings, fuming nitric acid is used for specialized reactions and for dissolving metals like silver and copper. However, it's got to be handled inside fume hoods with full protective gear. Even small drops on the skin can cause deep chemical burns due to rapid protein denaturation and dehydration. The characteristic yellow stains on skin from nitric acid exposure are well documented in clinical toxicology, but represent only one surface injury. Fuming nitric acid penetrates deeper and causes far more damage. These acids don't destroy everything. They do have limited effects on some fluoropolymers and certain high-nickel alloys, but their ability to oxidize, dehydrate, nitrate, and corrode makes them among the most broadly destructive corrosive liquids in industrial chemistry. Every known hazard is supported by decades of clinical and engineering data, and there's nothing mysterious about their destructive power. It is simply the combined force of strong acidity and extreme oxidizing strength acting together. Number 11. Sodium hydroxide. Sodium hydroxide, also known as lye or caustic soda, is one of the most widely used industrial chemicals. Sodium hydroxide is a strong base that reacts aggressively with many metals, organic materials, and biological tissues. When sodium hydroxide dissolves in water, it releases heat, a strongly exothermic process, and highly concentrated solutions can reach near boiling temperatures almost instantly. This heat, combined with the chemical reactivity of hydroxide ions, enhances all the corrosive effects. Hot, concentrated lye solutions can dissolve flesh, hair, fats, and protein rapidly. Sodium hydroxide is used in industrial meat processing to remove hair from animal hides and to dissolve organic residues from equipment. Now, lye destroys organic material through something known as saponification, a chemical reaction where fats and oils will break down into glycerol and soap. This reaction is scientifically well understood, and it forms the basis of traditional soap making. However, in uncontrolled environments, the same reaction can cause severe burns. Medical literature describes lye burns as deep and progressive because the ions penetrate tissues and continue reacting unless thoroughly neutralized and flushed out. It reacts with aluminum, zinc, and tin to produce hydrogen gas and metal hydroxides, and this reaction is strongly exothermic and can lead to dangerous pressure buildup if it happens in confined containers. Industrial accident case studies include multiple incidents where aluminum tools or storage vessels failed due to unnoticed lye contact. These are well documented in occupational safety databases. Commercial drain cleaners typically contain some solid lye or concentrated solutions because they can quickly dissolve organic matter like hair and grease. This is exactly the same chemical mechanism that makes the substance dangerous to the skin. Safety guidelines do warn explicitly against mixing lye-based drain cleaners with acids or bleach, as these combinations can produce heat or release chlorine gas. Protective gloves, goggles, and face shields are required because even small splashes can cause a lasting injury. The burns associated with it are extensively described in occupational medicine, and treatment protocols do show emphasized prolonged irrigation to remove the penetrated base. But despite all its destructive power, sodium hydroxide is chemically selective. Materials like stainless steel, some plastics like polyethylene and polypropylene, glass, and PTFE all resist attack. So as a result, lye is shipped and stored safely in containers made from those materials. Number 10. Potassium metal. So potassium is one of the most reactive elemental substances, especially when it comes into contact with water. Its destructive power comes from a combination of chemical reactivity, heat release, and hydrogen gas production. Potassium belongs to the alkali metal group with lithium, sodium, potassium, rubidium, cesium, and francium. As you move down this group on the table, the metals become increasingly reactive, and potassium sits in the range where reactions with water can become violent and sometimes explosive. When it touches the water, each potassium atom donates an electron to water, forming potassium ions, hydroxide ions, and hydrogen gas. This reaction releases a lot of heat, and because potassium has a low melting point, about 64 degrees Celsius, the heat generated is enough to melt the metal almost instantly. As the molten potassium spreads across the water surface, the reaction accelerates. Hydrogen gas bubbles form rapidly at the metal-water interface, and if the heat is sufficient, the hydrogen can ignite spontaneously. Potassium also reacts destructively with oxygen. When exposed to air, it rapidly forms potassium oxide, superoxide, or peroxide, which is yellow or purple crust that can ignite under friction or pressure. This is why potassium has to be stored under mineral oil or an inert atmosphere like argon. Contact with skin or biological tissue is pretty dangerous too because potassium reacts instantly with moisture, producing caustic potassium hydroxide. Medical case reports describe deep chemical burns from even small fragments of potassium containing damp surfaces. Potassium doesn't destroy everything, though, indiscriminately. Safe materials include certain hydrocarbons, paraffin oils, and inert gases, but its destruction of water-containing materials is nearly instantaneous. Every aspect of its reactivity is explained by fundamental chemical principles with no uncertainty about how or why the reactions occur. This destructive behavior has been repeatedly verified and rigorously studied, and it's universally respected. Number 9. Oleum. Oleum is also known as fuming sulfuric acid. It's a dense, highly corrosive solution of sulfur trioxide dissolved in concentrated sulfuric acid. It is significantly more reactive than regular sulfuric acid because it contains free SO3 molecules, which are powerful dehydrating and oxidizing agents capable of destroying organic tissue, metal surfaces, and a wide range of materials. One of oleum's most destructive characteristics, though, is the dehydrating ability of it. Oleum will strip water away from organic materials so aggressively that carbohydrates and proteins can carbonize on contact. Laboratory demonstrations show that sugar poured into oleum turns black and releases heat almost instantly. This is not an unusual reaction, it's the direct result of it breaking molecular bonds and extracting water content. Even a drop of water added to oleum produces an immediate exothermic reaction, in which sulfur trioxide hydrates to form more sulfuric acid. And while some materials like lead and certain stainless steels will resist this attack, many metals including zinc, magnesium, and aluminum corrode rapidly in oleum. Oleum's vapor pressure is another hazard too. Sulfur trioxide fumes above the liquid surface can react with moisture in the air to produce a dense white cloud of sulfuric acid aerosol. That cloud's corrosive to your skin, eyes, and respiratory tissue and can damage equipment, electrical components, and infrastructure. Because of that, storage tanks have to be airtight and equipped with scrubbers to neutralize escaping vapors. But in the chemical industry, oleum is used in the manufacture of dyes, explosives, pharmaceuticals, and detergents. It's also essential for the production of high-concentration sulfuric acid known as tower acid. These applications rely on oleum's ability to introduce sulfate groups into organic molecules, and handling it requires acid-resistant gloves, face protection, and specialized ventilation. Oleum doesn't attack everything. Materials like PTFE, glass, and certain high silicon cast irons are resistant, but it does destroy organic matter and unprotected metals. It earns its place on this list because it combines corrosive acidity, dehydrating power, fuming reactivity, and exothermic reactions into one of the most dangerous acids ever used. Number 7. Fluorine gas. Fluorine. It is the most reactive element in the periodic table, and when cooled below its boiling point of 188 degrees Celsius, it becomes a pale yellow liquid that retains all the aggressive reactivity of fluorine gas. Liquid fluorine is rarely handled outside of specialized industrial and research facilities. Fluorine atoms can break apart almost any stable bond by forming very strong fluorine-containing compounds. This includes metals, organic materials, silicon-based compounds, and many inorganic substances. Even noble gases like xenon can form fluorides under the right conditions. Liquid fluorine reacts violently with organic material. Most organic compounds contain carbon-hydrogen bonds, which fluorine breaks instantly, often producing enough heat to ignite the material. Laboratory demonstrations show immediate combustion when liquid or gaseous fluorine contacts substances like rubber, wood, oil, or even materials that are normally considered flame retardant. Metals, too, are vulnerable. Iron, stainless steel, copper, aluminum, and most other metals react with liquid fluorine. And when fluorine reacts with water or moisture, it produces a mixture of oxygen difluoride and hydrogen fluoride. Hydrogen fluoride is one of the most dangerous industrial chemicals. Liquid fluorine is used industrially in several niche but important applications. It's involved in the production of uranium hexafluoride for nuclear fuel processing, in specialty rocket propellant research, and in manufacturing high-performance fluorinated materials. Because of the extreme hazards, fluorine systems include redundant containment, remote operation, and inert gas purging. Fluorine doesn't destroy everything, though. Certain fully fluorinated polymers and select nickel alloys can withstand it, but nearly all other materials are vulnerable. Its ability to oxidize almost any element, destroy organic matter instantly, it makes it one of the most dangerous substances ever managed by chemists. Number 6. Osmium tetroxide. Osmium tetroxide is one of the most toxic agents used in modern chemistry. It's a crystalline solid at room temperature, but sublimes readily, producing fumes that can oxidize organic tissue. In high enough concentrations or when it's warmed up, it can become a powerful, highly corrosive liquid. Osmium tetroxide is a strong oxidizer. This gives the compound an extraordinary ability to accept electrons from other substances, particularly organic molecules. Osmium tetroxide reacts vigorously with carbon-carbon double bonds, but the same chemistry that makes it useful makes it dangerous because biological tissues contain so many of these double bonds. Contact with skin or eyes is medically serious, even at low concentrations. It penetrates tissue and oxidizes lipids and proteins in the cell membranes, causing deep burns, deep tissue damage, and potential vision loss. It also damages plastics, rubber, and many organic materials. Laboratory gloves made of latex or nitrile offer limited protection because it can permeate or degrade them over time. This is why researchers handling the substance wear thick neoprene gloves, lab coats, and face shields, and always work in chemical fume hoods. Metal surfaces aren't immune either. While osmium tetroxide doesn't react violently with most metals, it can oxidize metal surfaces with sufficient exposure, forming osmium dioxide or metal oxides that degrade any structural integrity. Glassware, however, is typically stable because it doesn't attack silica under normal lab conditions. Despite all the risks, though, it plays an indispensable role in research. It's widely used in electron microscopy as a staining agent because it reacts with lipids and creates high contrast. It doesn't absolutely destroy everything, though. Glass, PTFE, and select metals will resist attack, but when it comes to organic matter, and especially living tissue, it is one of the most destructive substances that can be handled in a lab setting. Number 5. Dimethylmercury. Oh, I don't like the sound of that one. Dimethylmercury sounds like one of the most dangerous chemicals ever synthesized. Unlike most mercury compounds, which are harmful primarily through chronic exposure or ingestion, dimethylmercury is actually toxic through skin contact, vapor inhalation, and even permeation through protective gloves. What makes it uniquely dangerous is its ability to cross biological barriers. The molecule is small, nonpolar, and highly lipid-soluble. Because of this, it's easily penetrating skin, latex gloves, and biological membranes. Studies have shown that dimethylmercury can permeate certain glove materials in under 15 seconds. That's way faster than most workers would realize. Permeability tests were performed after a well-known laboratory fatality in 1997 involving chemist Karen Wetterhahn. Her exposure led to the creation of new safety protocols in chemical labs worldwide. Once absorbed, dimethylmercury crosses the blood-brain barrier and accumulates in the central nervous system. It slowly decomposes into inorganic mercury species that bind tightly to any sulfur-containing proteins. Symptoms of dimethylmercury poisoning appear only after a long delay, sometimes months, and this delay is medically documented and makes the compound particularly insidious because exposure may go unnoticed until irreversible damage has happened. From a chemical perspective, though, dimethylmercury is stable in air and water, which might seem surprising given its toxicity. It doesn't decompose easily, and that stability allows it to remain intact long enough to accumulate inside living organisms. In research, dimethylmercury was once used in trace analysis of mercury isotopes because it could act as a reference standard in nuclear magnetic resonance imagery, and after the documented fatality and subsequent studies showing its glove permeability, nearly all labs abandoned its use. Today, it's widely recognized as too dangerous for routine handling. The ability to permeate protective barriers, the delayed symptoms, and its irreversible neurotoxicity place it among the most lethal and destructive substances ever handled by chemists. Number 4. Fluorine azide. Fluorine azide is an unstable and dangerously reactive inorganic compound. Even though it's been studied only in extremely controlled lab environments, its destructive behavior is thoroughly documented. It's a pale, volatile liquid near its freezing point, and an explosive gas slightly above it. What makes it so dangerous is a combination of two highly reactive chemical groups: elemental fluorine, the most reactive element in the periodic table, and the azide group, which is notoriously explosive in many compounds. Azides are already well known for their explosivity. The group readily decomposes into nitrogen gas and releases significant energy. When this unstable group is bonded to fluorine, the compound becomes extremely sensitive to heat, pressure, light, mechanical shock, and even minor impurities. When fluorine azide was first synthesized, a report noted that the compound can detonate spontaneously with no apparent trigger. Researchers observed explosions occurring during storage, transfer, and even while just cooling the compound. It reacts violently with many materials, particularly organic compounds, and most molecules contain hydrogen and carbon, which fluorine azide breaks apart instantly due to its extreme oxidizing power. Reactions with oils, waxes, rubber, or even just dust particles can trigger decomposition. Its reactivity with metals is similarly destructive. It can attack common metals and metal oxides, forming metal fluorides and releasing nitrogen gas. For this reason, fluorine azide must never be stored in metal containers. Researchers instead used a specialized fluoropolymer or glass vessel, although those even offer a narrow margin of safety. Despite its dangers, though, it's been studied for fundamental research into nitrogen-fluorine bonding and high-energy compounds. It's got no commercial applications, and it's not used in industry due to its unpredictability. And handling guidelines in the scientific literature emphasize remote manipulation, cryogenic temperatures, and extremely small quantities, often milligrams or less. It doesn't destroy everything, of course. Fluorinated polymers like PTFE and some inert gases are stable around it, but the combination of explosivity and strong oxidizing power, and the extreme reactivity of both fluorine and the azide group, makes it one of the most dangerously destructive substances. Number 3. Perchloric acid. Perchloric acid is a strong acid and it's a powerful oxidizer. It becomes dangerously destructive when heated or concentrated. Unlike many acids that act primarily as proton donors, this one's destructive power increases as the temperature rises because it transitions from a simple acid into an energetic oxidizer. At room temperature and low concentrations, perchloric acid behaves similar to other mineral acids like nitric or sulfuric. It's corrosive but relatively stable. However, when heated above approximately 160 degrees Celsius, or concentrated roughly above 70%, its behavior changes. The acid begins to dehydrate, forming a reactive perchlorate species that can oxidize organic matter rapidly. When it encounters organic materials like paper, oils, wood, textiles, solvents, it can react explosively. Over time, vapors will form perchlorate salts, which are shock-sensitive and can detonate if disturbed. Several well-documented explosions in the mid-20th century led to major changes in lab design. Today, fume hoods used for perchloric acid must include washdown systems that continually dilute and rinse away any perchlorate deposit. It's also destructive to many metals when hot or concentrated. It dissolves stainless steels, aluminum, copper, and iron by oxidizing metal surfaces and forming perchlorate salts. The salts, of course, are unstable, adding further hazards, and materials like glass, PTFE, and certain high-nickel alloys do resist attack, which is why they're used for storage and handling. Industrially, perchloric acid is used in analytical chemistry, especially for digesting samples before elemental analysis. This is because it can break down stubborn matrices, turn them into carbon dioxide and water. It's also used in certain rocket propellants and metal surface treatments. All the applications do require strict safety measures. At room temperature, though, and moderate concentrations, it's actually less reactive than nitric or sulfuric acid toward certain materials. But when it becomes concentrated or heated, its oxidizing power makes it one of the most dangerous laboratory acids. Number 2. Polonium-210. Polonium-210 is one of the most destructive substances known because it damages living organisms from inside at the atomic level. Unlike corrosive acids or reactive chemicals, polonium-210 destroys biological tissue through intense alpha radiation. It's a radioactive isotope produced in nuclear reactors by bombarding bismuth-209 with neutrons. It's got a half-life about 138 days, which means it decays relatively quickly and releases a large amount of energy per atom. Almost all that energy is released as alpha particles, helium nuclei that's traveling at high velocity. These alpha particles cannot travel far, but they deposit enormous energy into whatever they hit. Outside the body, polonium-210 is not extremely dangerous. The alpha particles can't penetrate skin, clothing, or even a sheet of paper. But inside the body, where tissues and organs have no natural shielding, the destructive power becomes overwhelming. Alpha particles deposit their energy over extremely short distance, causing dense ionization that will break DNA, damage cell membranes, and disrupt vital molecules. This kind of damage has been studied extensively in radiobiology, and alpha particles are known to have a high linear energy transfer, meaning they cause more biological harm per unit of absorbed radiation compared to many other types of radiation. The greatest danger comes from ingestion or inhalation. Polonium-210 can enter your bloodstream, accumulate in organs, and deliver extremely high localized radiation doses. Even a few micrograms, an amount invisible to the naked eye, can be lethal. Nuclear regulatory agencies around the world classify polonium-210 as one of the most radiotoxic substances. The 2006 poisoning of Alexander Litvinenko in London is the most thoroughly documented case of polonium-210 poisoning in history. Over several weeks, he suffered progressive organ failure and bone marrow destruction, consistent with massive internal alpha irradiation. Investigators later detected polonium contamination at multiple locations he had visited. This case is frequently referenced in radiological safety literature and illustrates the real-world lethality of this isotope. Contamination with polonium-210 does pose long-term hazards. If particles become airborne, they can be inhaled, and because the isotope tends to bind to dust and fine particulates, it can travel through ventilation or settle on surfaces. Decontamination is challenging and requires the removal of contaminated materials, not simply washing or filtering. Radiological cleanup documentation shows that even small spills demand multi-step monitoring and measurement protocols. Every aspect of its danger, from its decay pathway to its biological effect, is supported by decades of research in nuclear science and medical toxicology. Number 1. Thionyl chloride. Thionyl chloride is one of the most destructive chemical reagents in laboratory chemistry because it reacts violently with water, moisture, organic material, and many common surfaces. It's a colorless to pale yellow liquid with a sharp, irritating odor. It's widely used as a chlorinating agent because it can replace hydroxyl groups in alcohols with chlorine atoms. That reaction produces hydrochloric acid and sulfur dioxide as byproducts. Both these gases are highly corrosive and toxic, and their release contributes to the destructive nature of this chemical. One of the most dangerous characteristics of thionyl chloride is the way it reacts with water. Even small amounts of moisture trigger an immediate, vigorous reaction that produces a mix of hydrochloric acid and sulfur dioxide gas. These gases dissolve in moisture on surfaces in the air or form highly acidic droplets that are capable of corroding metal, degrading plastics, and burning biological tissue. Numerous lab accidents recorded in chemical safety databases involve improper quenching or dilution of it with water. Thionyl chloride also reacts destructively with many organic materials. When it contacts alcohols or other acids, it can produce reactive intermediates that decompose violently if the reaction isn't controlled. Without proper handling, reactions can release large volumes of corrosive gas. Metals are vulnerable too. It corrodes iron, aluminum, copper, and most common alloys. Even stainless steel can degrade when exposed to the substance or its decomposition gases. Transport, of course, requires regulations that are sealed, moisture-free containers that are equipped with pressure relief mechanisms. Direct skin contact causes severe chemical burns because it reacts with moisture on the skin to generate that hydrochloric acid. Occupational exposure guidelines from agencies like OSHA list extremely low permissible exposure limits for both gases, which shows this documented toxicity. Sulfur dioxide irritates your respiratory tract, while the hydrochloric acid vapor causes deep, painful burns to mucous membranes. Despite the hazards, though, it's got legitimate industrial uses. It is essential in the production of pharmaceuticals, agrochemicals, dyes, and some advanced materials. It plays a role in manufacturing lithium chloride batteries, which rely on the chemical's ability to undergo controlled reduction reactions, and in every industrial setting, though, strict engineering controls, dedicated ventilation, sealed processing systems, and emergency wash stations are all mandatory. Everything known about thionyl chloride's hazards is documented in peer-reviewed chemical literature and industrial safety guidelines. It's one of the most consistently destructive liquids that's used in modern chemistry, and it deserves its place at the top of this list.